a 240-volt 3-phase 4-wire electrical service, the ground wire should not have current flowing through it under normal operating conditions. Its primary function is to provide a low resistance path for fault current to return to the source, which facilitates the operation of overcurrent protection devices like circuit breakers or fuses. The presence of current in the ground wire typically indicates an electrical problem that needs investigation. Several factors can cause current to flow on the ground wire. Firstly, a ground fault occurs when one of the hot wires comes into direct contact with a grounded metal object of the ground wire itself. This creates a low resistance path for current to flow through the ground wire back to the source, potentially causing a large amount of current to flow, which should trip the circuit breaker or fuse. Secondly, a neutral to ground fault involves a connection between the neutral wire and the ground wire at a point other than the designated single point bond at the service entrance. This can cause current to flow on the ground wire, as the neutral current seeks an alternate path back to the source. Thirdly, an unbalanced load in a three-phase system means that the current drawn on each of the three phases is not equal. While some imbalance is normal, a significant imbalance can cause a portion of the neutral current to flow through the ground wire, especially if there are neutral to ground connections downstream from the service entrance. Fourthly, induced current can occur when the ground wire runs parallel to current-carrying conductors. The electromagnetic fields generated by these conductors can induce a small amount of current in the ground wire. While this is usually minimal, it can sometimes be measurable, particularly in long runs of wire or in areas with high electromagnetic interference. If current is detected on the ground wire, several safety precautions should be taken. 1. Immediately turn off the power to the affected circuit or equipment at the main electrical panel. 2. Contact a qualified electrician to diagnose and repair the problem. Do not attempt to troubleshoot or repair the electrical system yourself, as this can be extremely dangerous. An electrician will use specialized equipment to identify the source of the ground current and correct the underlying issue. One possible cause for a reading on the ground wire is induced current. The ground wire can act like an antenna and pick up stray electromagnetic fields from nearby electrical equipment or wiring. The amount of induced current is usually small, but it can be enough to register on an amp meter, especially a sensitive one. Even if induced current is suspected, it is still important to have the system inspected by a qualified electrician to rule out any other potential problems. To further elaborate on ground faults, they are dangerous situations that can lead to electrical shock or fire. The purpose of the grounding system is to provide a safe path for fault current to flow back to the source, allowing the overcurrent protection device to trip and to energize the circuit. If the grounding system is not properly installed or maintained, a ground fault can result in a dangerous voltage on metal parts of equipment, posing a shock hazard. Neutral to ground faults are often caused by wiring errors or insulation damage. The neutral wire is intended to carry the unbalanced current from a three-phase system back to the source. However, if the neutral wire is connected to the ground wire at multiple points, it can create a parallel path for current to flow, leading to current on the ground wire and potential voltage drops in the neutral conductor. This can also cause sensitive electronic equipment to malfunction. Unbalanced loads can occur for a variety of reasons. In a commercial or industrial setting, it may be due to uneven distribution of lighting, equipment, or machinery across the three phases. In a residential setting, it could be due to different appliances being used on different circuits. While a small amount of imbalance is normal, a large imbalance can overload the neutral conductor and cause current to flow on the ground wire. To minimize unbalanced loads, try to distribute the electrical load evenly across the three phases. This may involve rearranging circuits or moving equipment to different phases. Induced current can be minimized by keeping ground wires as short and direct as possible, and by avoiding running them parallel to current-carrying conductors for long distances. Shielded cables can also be used to reduce electromagnetic interference. It is important to note that the National Electrical Code, or NEC, provides detailed requirements for grounding and bonding electrical systems. These requirements are designed to ensure the safety of people and property by providing a low impedance path for fault current to flow back to the source. Some relevant NEC sections include 250.4, which covers general requirements for grounding and bonding, 250.24, which covers grounding requirements for separately derived systems, and 250.166, which covers sizing requirements for grounding electrode conductors. The NEC also provides specific requirements for grounding different types of equipment, such as motors, transformers, and generators. It is important to consult the NEC and other applicable standards when designing, installing, or maintaining an electrical system. Remember that working with electricity can be dangerous, and it is always best to consult a qualified electrician if you have any questions or concerns. A qualified electrician will have the knowledge, skills, and equipment to safely diagnose and repair electrical problems. They can also ensure that your electrical system is installed and maintained in accordance with all applicable codes and standards. Some additional points to consider when troubleshooting ground current problems include, firstly, checking the grounding electrode system. The grounding electrode system consists of the grounding electrode, such as a ground rod or metal water pipe, and the grounding electrode conductor, which connects the electrode to the main electrical panel. This system provides a connection to earth, which helps to stabilize the voltage and provide a low impedance path for fault current. Make sure that the grounding electrode is properly installed and that the grounding electrode conductor is securely connected. Secondly, inspecting the neutral conductor. The neutral conductor is the return path for current in a three-phase system. It is important to ensure that the neutral conductor is properly sized and that it is not overloaded. An overloaded neutral conductor can cause voltage drops and current to flow on the ground wire. Thirdly, checking for loose connections. Loose connections can create resistance in the electrical circuit, which can cause voltage drops and current to flow on the ground wire. Make sure that all electrical connections are tight and secure. Fourthly, using a ground fault circuit interrupter, or GFCI. GFCIs are designed to protect people from electrical shock by detecting small amounts of current leakage to ground. If a GFCI detects a ground fault, it will quickly trip the circuit and interrupt the flow of electricity. GFCIs should be installed in areas where there is a risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. Fifthly, using an amp clamp meter to measure current. An amp clamp meter is a device that can measure the current flowing through a wire without having to disconnect the wire. This can be a useful tool for troubleshooting ground current problems. To use an amp clamp meter, simply clamp the meter around the wire you want to measure. The meter will display the amount of current flowing through the wire. When measuring ground current, be sure to measure the current at multiple points along the ground wire to identify the source of the current. Sixthly, using a multimeter to measure voltage. A multimeter is a device that can measure voltage, current, and resistance. It can be a useful tool for troubleshooting electrical problems. To use a multimeter, connect the meter leads to the points you want to measure. The meter will display the voltage, current, or resistance between the points. When measuring ground voltage, be sure to measure the voltage between the ground wire and a known good ground, such as a metal water pipe. A high voltage reading indicates a ground fault. Seventhly, verifying proper bonding. Bonding refers to the practice of connecting all metal parts of an electrical system together to create a low impedance path for fault current. This helps to ensure that all metal parts are at the same voltage potential, which reduces the risk of electrical shock. Make sure that all metal parts of your electrical system are properly bonded together, including metal conduits, metal enclosures, and metal water pipes. Eighthly, conducting an insulation resistance test. An insulation resistance test, also known as a Megger test, is used to measure the resistance of the insulation on electrical wires and cables. This test can help to identify insulation damage that could be causing ground faults. To conduct an insulation resistance test, use a meggermeter, which is a specialized instrument that applies a high voltage to the insulation and measures the resulting current. A low insulation resistance reading indicates insulation damage. Ninthly, understanding harmonic currents. Harmonic currents are currents that are multiples of the fundamental frequency of the power system, which is typically 60 Hz. These currents can be generated by nonlinear loads such as electronic devices, variable frequency drives, and uninterruptible power supplies. Harmonic currents can cause a variety of problems in electrical systems, including overheating of conductors, transformers, and other equipment. They can also cause voltage distortion and interference with sensitive electronic equipment. Harmonic currents can contribute to ground current problems, as they can flow through the grounding system. Tenthly, documenting all findings. When troubleshooting ground current problems, it is important to document all of your findings, including the date and time of the measurements, the location of the measurements, the equipment used, and the readings obtained. This documentation can be helpful for tracking down the source of the problem and for communicating with other electricians or engineers. Remember to consult with a qualified electrician for any electrical issues that you are not comfortable handling yourself. Electricity can be dangerous, and it is always best to err on the side of caution. By understanding the causes of ground current and taking appropriate safety precautions, you can help to ensure the safety and reliability of your electrical system. Furthermore, keep in mind that the specific requirements for grounding and bonding can vary depending on the local electrical codes and regulations. It is important to consult with your local electrical inspector or a qualified electrician to ensure that your electrical system meets all applicable requirements. Continuous monitoring of the electrical system can also help detect ground current issues early on. This can be achieved using specialized monitoring equipment that can measure ground current in real time and provide alerts if the current exceeds a certain threshold. Regular inspections and maintenance of the electrical system can also help prevent ground current problems. This includes checking for loose connections, inspecting the grounding electrode system, and testing the insulation resistance of wires and cables. Additionally, consider the impact of adding new equipment to the electrical system. New equipment can introduce new loads and harmonic currents, which can contribute to ground current problems. Before adding new equipment, it is important to assess the impact on the electrical system and to make any necessary adjustments to the grounding and bonding system. In summary, dealing with ground current in a 240-volt 3-phase 4-wire service requires a systematic approach. This involves understanding the fundamentals of grounding and bonding, identifying potential sources of ground current, taking appropriate safety precautions, and consulting with a qualified electrician when necessary. By following these steps, you can help to ensure the safety and reliability of your electrical system. Remember that proper grounding is not just a matter of code compliance. It is a critical safety measure that protects people and property from electrical hazards. By investing in a properly designed and maintained grounding system, you can help to prevent electrical shocks, fires, and equipment damage. The information provided here is for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician for any electrical work or troubleshooting. The complexities of electrical systems require expertise and experience to ensure safety and compliance with all applicable codes and regulations.